Hello, my name is Neil. I'm the second one in the list. The first one is my boss, Julio, and the leader of this innovation process in Brazil. I'm a former PhD student of DTU, actually from Ildefonso's group, and right now I'm responsible for the strategic management and planning of the high-speed optical networks division in CPQD. The target of my presentation is to talk to you about who we are, what we do in Brazil, how we see the path to the future optical networks, which is the title of this session, and to open channels of communications with you for cooperations. Basically, Brazil is growing up very fast, and we have a lot of things to do. So I'm open for talking after this short talk. So this is the summary of the talk. First, I'm going to start with the motivation. Then I'm going to briefly explain the CPQD strategy on optical communications. Inside this strategy, I will talk about high-speed optical transmissions, the technology we are developing right now, optical networking, our advances in optical networks, microelectronics for coherent transmission, and integrated photonics. At the end, I'm going to conclude the talk. So we have in front a big and interesting challenge. The World Cup is coming. And in 2 years from now, we will have the Olympics. So basically, we have two big problems in Brazil right now. First, deployment of optical networks, and second, optimization of optical networks. So in our context, in the context of Brazil and South America, future networks are a little bit behind the step we are discussing here in the workshop, but really important for society because we need to build the fiber network. Of course, it exists, but it's not going to be enough. So this is the main motivation. In 2014, it's expected to have 6,000 kilometers of fibers in Brazil. We are still working on. And the rate right now transmitted in Brazil is around 40 gigabits per second. So we have the big challenge in CPQD, which is the Research and Development Center of Brazil, the biggest one, the place where I work, to develop technology and transfer this technology to Brazilian industry of 100G systems, 400G systems, and 1 terabit systems. So this is the motivation. Who we are? We are a private foundation. We are driven by the concept of innovation, and this concept of innovation is composed of three parts. We do research, we do as well development, and we must transfer this technology to the industry. We must close the cycle. In terms of research, CPQD has a more or less 30 years history, papers, patents in development. We are right now very strong in amplifiers, WSS, ROADMs, and in market, we have also transferred several versions of the amplifiers to the national industry in Brazil. Right now, we got the leadership of the 400G project, white paper project in OIF, so we are also in standardization organizations. So this is our nature, research, development, and market. Few examples about what we do in CPQD. One of them, and in my opinion, this is my personal opinion, this is the most successful one, it's amplifiers. So this evolution you see here, in this sense, it's more or less evolution after between 8 and 10 years. So right now, my team is working in the final prototype to transfer to PATTEC, which is our Brazilian company of optical systems, of a hybrid EDFA Raman amplifier. This prototype is going to be delivered to the company in 2 months from now. Another example I want to show to you is the ROADM platform. So right now we can also control this platform. We are in the path of cognitive networks. I'm going to briefly mention these advances in cognitive networks in a few minutes. One more example is the 100G coherent optical module we are working on. But to do that, we need to add some more functions or lines inside our process. Before or until 2 years ago, we were only working in optical systems. So since 2 years, we are also working in microelectronics and integrated photonics to be able to produce a prototype of 100G module. I'm going to mention this as well. So basically, we are not a university doing just proof of concepts. We are not a company producing. We are something in the middle. We are the bridge between universities and companies. So exactly where we are in CPQD, we are watching what's going on in basic research, and we try to filter out these ideas, taking as a final target production, and we try to perform prototypes. We try to perform experimental proof of concepts and produce the prototype to make this bridge between the university or academy and the industry. So what's the strategy until now? As I told you before, we were working in amplifiers, RODAM, some GPON, optical systems basically, doing experiments in the lab. But right now we recognize that it's necessary to do something more to keep this evolution that we draw here. If we don't adapt this strategy of developing microelectronics or developing integrated photonics, we were not able to continue this evolution. So that's why in our strategy, we are thinking right now in making modules, so bringing microelectronics industry to Brazil, and designing and also building, creating integrated photonics. So that's our strategy from now. So now let me give to you some examples about what we have done until now. I'm going to start with optical systems. So we have terabit systems right now in our lab, different configurations. So we can work with QPSK, 16QAM, and higher order modulation formats. We have also super channels in CPQD. So in terms of optical systems, we are close to the state of the art, or just we have reached the state of the art. And for example, in this first example, this is some technology we are trying to optimize to produce our prototype. We think it's possible to achieve 400 gigabits per second with some overhead for FEC, with two optical carriers in a 16QM modulation format. So the interesting part in this experiment we performed one and a half years ago, it's the grid. So we can achieve, or we achieved 400 gigabits per second in 75 gigahertz bandwidth. As a natural evolution of this experiment, we also achieved 1 tera using super channels. We transmit 100 kilometers this super channel. And here, I just want to summarize the main characteristics of this experiment. So 28 gigabaud, 16 QAM, 224 gigabits per second, 6 bits per hertz as a spectral efficiency, and after 1,000 kilometers. So we achieved in our technology some devices, some optical systems for metropolitan applications. We also have developed a flexible transmitter for terabit applications. So since we can have 16 QAM and QPSK, we adjust some of the functions inside the optical system to switch between this QPSK and 16 QAM according to the needs of a potential final user. So in this case, by using the same hardware, we can have a system for metropolitan applications and for long-haul applications. Different bit rate. One is for QPSK, the other one is for 16 QAM. And the reach we achieved in our lab was almost 5,000 for long-haul networks using QPSK and 900 kilometers for metropolitan networks. This is something I can talk to you later. So now let me jump to the advances in optical networks. So right now we have this test bed in our lab. So we are able also to emulate experimentally an adaptive network. So we can control the WSS. We can control as well the optical amplifier. So this is a test bed I would like to offer here for experimental tests. So if you have ideas, if you want to test something about cognitive networks, CPQD is ready to take these ideas and reproduce these ideas. So one of the interesting examples here is our cognitive amplifier. So since amplifiers, as I showed you a few minutes ago, is one of our main examples in terms of innovation, so doing this cycle of innovation, we have access to all components of the system. So in the last year, we have been exploring how to optimize the operational point of the amplifier. So we have characterized our amplifiers, and right now we have a strategy to integrate cognitive functions into the amplifier. I hope we can show to the optical community, ECOC, OFC, I don't know, our cognitive amplifier very soon. I don't know if we will be able to do it this year, but I'm pushing my team to have results for next year. So we also have an adaptive flexible transponder based on that concept I briefly showed to you about having a single hardware to jump from QPSK to 16QM. We have also integrated this concept to our optical network. This is the first part about optical systems. Now let me go to the second point in our strategy, which is microelectronics. We don't have a foundry in Brazil, but we will have very soon a foundry. Right now we are working in design. So our first project in microelectronics is to have our first microelectronic chip, Brazilian microelectronic chip for 100G and 400G systems. So just let me briefly show here the main architecture of the receiver of this ACDSP. So in my division, in Campinas, Campinas is the city of CPQD, it's close to Sao Paulo, just 1.5 hours from Sao Paulo. We have developed these blocks in MATLAB level, just as almost all groups working or starting working in digital communications. And we have mounted the whole flow up to the gate level. So we have the proof of concept in the lab. So we have offline data, and we process with MATLAB or other platform like that. And then we start converting this MATLAB code up to the gate level. So there are several steps. So we have to create high-level synthesis. Then we have to go to RTL. We have the whole flow in Campinas. The only missing part is the last step of the flow, which is the silicon part. So when you print this RTL file into a chip. So right now we have a partner here in US doing this for us. It's expected to have our first Brazilian chip for the second quarter of next year. It's also very important in our strategy, the integrated photonics. So we are learning. We are starting right now. We have a team working in designs. This is the first design we sent to OPSIS. We have already received the chip, and the guys are characterizing this chip in the lab. I'm not expert in integrated photonics, so sorry if I can't answer your questions about integrated photonics. But in this design, we could integrate in this chip modulators, some receivers, and some splitters. This is more or less the idea we have, Julio and the management team in CPQD Mine. Right now, we are optimizing the design of the DP-QPSK receiver in silicon photonics, the DP-16QM modulator, and we are starting a line working in amplifiers for submarine transmission. The next step is going to be 16QM receiver, NWDN, DP-QPSK modulator, and so on. So this is our dream, and we are walking through the dream. This is the design just for 400G transceivers. We have already finished part of this, and we have sent already to a second run in OPSIS this design. So it's expected to receive in 6-7 months from now the second chip design in CPQD for characterization and testing. So this is a learning process. We design, we send, we receive, then we characterize and we optimize the design. I just want to, very close to the end of my presentation, to show to you some of our some pictures of our lab over there. So this is the integrated photonics lab for characterization. With this, my intention with this picture is just to show the capabilities we have already in CPQD. So this is the final layout of the integrated photonic chip we sent to the second round in OPSIS. Well, just to finish the presentation, I want to summarize in this slide what we are doing right now in Brazil. So we started in transmission, so in optical systems. So we have these systems in our lab. Then we moved to ASIC DSP. We moved to electronics and integrated photonics to have our own module and then integrate to the optical network. It's very important in our countries, in Brazil, Colombia, and from Colombia. It's quite important to generate value to the society. So CPQD is in charge of this responsibility, at least in Brazil. So research, development, market, and then generate value for the society. This is the talk I have prepared for you, and questions, comments, and are welcome. Thank you.